Good morning, everybody. Welcome back to Calc 2. Plan for today is we're going to finish off our discussion of sequences. And if we have time, we'll jump into Standard 11 towards the end of class, start talking about infinite series, which is the sort of infinite sums we were talking about last Friday. As far as office hours go, I'm going to have to cancel my office hour this afternoon, unfortunately. So instead I'll hold an extra office hour tomorrow morning. So today I'll have office hours from 11 to noon, and tomorrow we'll have morning office hour from 10:30 to 11:30, and an afternoon office hour from 1 to 2. And as far as homework goes, I didn't post any new web work problems, but you still have a set to Friday night. And we will have a quiz Friday over standard 10. How y'all doing? Professor shouldn't be yawning during class. It sets a bad precedent. So, one day, a farmer, an engineer, a physicist, and a mathematician. Let's draw these all on the board. So here, this will be the engineer. This will be the physicist. Be our mathematician. Farmer one day enlisted the help of these three people to help fence off the largest possible area with a fixed amount of fence. So engineer goes first, says with his fence what he's going to do is he's going to build a circle. Builds a big circle and says that he has made the most efficient design for maximizing area enclosed within that small amount of fence. The physicist goes next. And what the physicist does is he builds a line, straight line with his fence, and he says, we can assume that this fence is infinite, and thus I've made off of a section of fence that has fenced off the entire world. Clearly I have the best design. Mathematician goes next. Mathematician builds a tiny fence in square around himself and says, I declare myself to be on the outside of this fence. Therefore, I have fenced in the maximum possible area. Literally all the earth outside of this little square. Moral of the story is, even mathematicians are weird. Okay, so when we left off last time, we had started to talk about sequences and what it means for a sequence to converge or diverge. Or a sequence was just like an ordered list of numbers that goes on forever. And we said that a sequence converges to L or just the shorthand, a sub n, and then that little arrow, L. If for large values of n, as n grows larger and larger, we want the values in our sequence to get closer and closer to this value, L. It's often labeled as L to refer to the fact that we're taking the limit of a sequence, like a limit as n goes to infinity. And so last time we looked at some examples and said things like, hey, if you have a sequence like b sub n equals 1 over 2 to the n, which gives us a sequence that's like a half, a fourth, an eighth, a 16th, etc., etc. Does that sequence converge? I think I'm getting some mixed signals from you back there.
Yes, it does converge.
What does it converge to?
0.
Yeah, so this one we can say converges to 0. Because as we go further and further out in the sequence, the individual terms in the sequence are going to be getting closer and closer and closer to 0. The distance is going to shrink down to nothing, even though 0 itself doesn't ever appear in the sequence. How about this one? C sub n is negative 1 to the n, which is the sequence where we have negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1, going on forever. What did we say about that sequence? Piggy?
It diverges because it's just oscillating, but they're actually like approaching everything.
Yeah, that this sequence, even though it has infinitely many ones and infinitely many negative ones in it, doesn't ever approach and stay close to a single value. So we say the sequence is divergent or diverges because there is not one single value that sequence approaches for as n gets larger and larger. And last time I'd given you all a bunch of sequences to look at. We talked through several of them, and we left things off with a couple sequences from that list to still look at. So, without further ado, how about this sequence? D sub n is defined to be cosine of n pi over 2. Let's put it to a show of thumbs. Thumbs up for converge, thumbs down for diverge. Thumbs sideways for Dr. Ursula's way too early in the morning for this. To show. Okay, Kate, why do you say diverge?
Because it's a cosine function, kind of like the 1, negative 1, it's just going to oscillate back and forth, and it's never actually going to reach it.
Yeah, this is going to be some very oscillatory. So if we start plugging in values of n, we'll get like cosine of pi over 2, cosine of 2 pi over 2, cosine of 3 pi over 2, cosine of 2 pi, etc., etc. And if we take a look at our unit circle, we're basically saying, hey, take all 4 of these points, take the x-coordinate of that point to get cosine of pi over 2, pi, 3 pi over 2, 2 pi, etc. And then if you plug in all of those x-coordinates into an infinitely repeating sequence, what ends up happening? Cosine of pi over 2 is 0. Cosine of pi, negative 1. Cosine of 3 pi over 2, down here, as an x-coordinate of 0. Cosine of 4 pi over 2, or 2 pi, has an x-coordinate of 1. And then it keeps repeating itself. 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, going on forever. And as Kate points out, for very similar reasons to why that negative 1 to the n sequence over there diverged, this one is also going to diverge as well due to its oscillatory behavior. It never gets close and stays close to a single number. It's kind of jumping back and forth between 0, 1, and negative 1. So how about this sequence? E sub 1 equals 1. For n greater than 1, E sub n is negative 1 plus E sub n minus 1 all over 2. So what's different about this sequence from all the other sequences we've looked at thus far?
It's using itself in the definition of the sequence.
Yeah, unlike this D sub n here, or B sub n, or C sub n, all of these sequences, these first 3, are all sequences that have explicit formulas. That, like, if you wanted to plug in n equals 30, find the 30th term in each of these sequences. 1 over 2 to the 30, negative 1 to the 30th power is 1. Cosine of 30 pi over 2, that's what? Cosine of 15 pi, which is negative 1. Here, if I wanted to find the 30th term in the sequence, it would be negative 1 plus the 29th term all over 2. Okay, what's the 29th term? Well, that's going to be negative 1 plus the 28th term all over 2. And the 28th term is going to be negative 1 plus the 27th term all over 2. And so on. Anybody know what we call this type of sequence that's kind of defined in terms of itself? It's It's a term that shows up a lot in like computer science.
Recursive.
Yeah, this is an example of what's called a recursive sequence. Which is a sequence that's defined in terms of itself, as Aiden put it. Or in a self-referential way. Self-referential here meaning to the fact that if you wanted to look at how the 30th term is defined, it's defined in terms of a different term in the sequence, the 29th term. Whereas over here, if you were to take the 30th term in this sequence, you don't need to know any of the other terms in the sequence to find out what the 30th term is. You would just need to plug in 30 for n and 1 over 2 to the 30th, which really is a very, very small positive number. You might think of any other famous recursive sequences that are defined in terms of themselves. There's one really famous one that kind of shows up a lot in nature that starts with the letter F. You know what sequence I'm thinking of? Okay.
The Fibonacci sequence.
Yeah, Fibonacci sequence is probably the most famous example of one of these recursive sequences. Where the Fibonacci sequence, usually what you do is you say the first term you're going to set to be equal to 1. The second term you also set to be equal to 1. And then you say for n greater than 2, you define a sub n to be the sum of the previous 2 terms in the sequence. So for instance, you would get a sub 3 is going to be a sub 2 plus a sub 1, which is 1 plus 1, or 2. A sub 4 would be the sum of its previous 2 terms, a sub 3 plus a sub 2, which would be 2 plus 1 is 3. And if you were to try and write the sequence out, you would get something like 1, 1, 2, 3, 5, 8, 13, 21, etc., etc. Where to get from your next term in the sequence, you have to add the previous 2 terms. This is a fun little sequence. Shows up if you're sneaky about it all over the place. You can look at, if you're in biology, you can ask your biology professors about how a Fibonacci sequence shows up in like breeding patterns in rabbits. There's a lot of cool ways in which Fibonacci sequence and these recursive sequences in general will show up in math. Questions, comments, concerns thus far? Here's something else that's recursive. Remember our good old friend, the factorial function? Where we said n factorial is going to be n times n minus 1 times n minus 2 times n minus 3, all the way down to 1. You can actually define the factorial function using a sort of in a recursive way as well. You can say, I'm going to define 1 factorial to be 1, and for n greater than 1, n factorial is defined to be n times n minus 1 factorial. And that would actually give us a sort of recursive way to define the same factorial function that we've seen before. Because if you want to look at 2 factorial, according to this definition, you would take 2 times 2 minus 1 factorial, which is 2 times 1 factorial, which is just 2 times 1 or 2. You could then take 3 factorial to get 3 times 3 minus 1 factorial, which is 3 times 2 factorial, which comes out to 6, and so on. And this kind of gives us maybe a little bit of a more shorthand way of writing out a definition for the factorial function using this idea of recursion, defining some mathematical expression in terms of previous versions of itself, or self-referentially. N factorial is defined in terms of n minus 1 factorial. Or, with like this sequence, the nth term in the sequence is defined in terms of the n minus first term in the same sequence. So, how about the sequence? The E sub n sequence from the packet. Throwing a lot of examples and stuff at you, but we haven't actually talked about whether or not this sequence converges yet. So, by a show of thumbs, y'all think this one converges or diverges? Seen a lot fewer thumbs. Hope something didn't happen. Hope they didn't get caught in a mouse trap or something out there. Reagan, you feel pretty unsure about this one?
Yeah.
James, what were your thoughts?
I thought that it is convergent, or
Okay.
it does converge.
How did you determine that?
So you start with the 1,
Mhm.
and then you move on to the next term, where you plug in -1, or so then it's -1 plus 1 over 2. So then it's just 0.
Okay.
And then after that, you just plug in 0, so you get -1/2 for the third term.
Sounds good.
And then after that, you plug in the -1/2, and then that just winds up as being -3/4.
Okay, let's see, we get -1 minus a half is -3/2 over 2 is -3/4.
Mm-hmm. And then after that, it's -7/8.
Okay, so James, it sounds like you just kind of started plugging in numbers and looked for a pattern.
Yeah, and then it's probably around when I got to the 5th term where I noticed a pattern of how to find the next one easily. Because then it's just the denominator times that, or wait, I need to think of how I thought. Oh yeah, so you're adding 1 to it. So with the -7/8, you're adding 8 or -8/8 to it. So then that would be negative. That would be -15. Yeah, 15 over 8, and then you always multiply the denominator by 2.
Ah, interesting.
Yeah, so then on the numerator it's always 2 times the numerator minus 1, and the denominator is always 2 times the denominator. So that always leaves you with a number that's always 1 smaller on the top than it is on the bottom, like negative, and then it slowly progresses towards -1.
Interesting. So you claim that the sequence converges to -1?
Mhm.
Let's see, Gabe, is that what you got as well? I think you had your hand up, or thumb up. What do y'all think about this? Other than James and Gabe. We have a sequence that goes 1, 0, -1/2, -3/4, -7/8, -15 over 16. Does it look to everyone like that's approaching -1? Next term would be like -31 over 32, -63 over 64, I'm gonna stop there.
Yeah.
I would agree. Sequence does converge to -1. Here's a question. Anybody think of a way to show that this sequence goes to -1 without just plugging in 10 terms and hoping that there's some sort of pattern, or hoping that the pattern doesn't break. So if I have two numbers, let's say A and B, how would I find the midpoint of those two numbers? The number that's exactly halfway in between A and B. Anybody remember the midpoint formula? All right. How about if we had 6 and 10? Taylor, what number is exactly halfway between 6 and 10? Yeah, that one would be 8. All right, if we had a number that was halfway between 12 and 20. Allie?
16.
Yeah, that would be 16. If you notice, what happens if you add 6 and 10? David?
16.
Divided by 2 is 12 plus 20 is
32.
divided by 2 is
16.
the number that's halfway between an arbitrary A and an arbitrary B is similarly A plus B over 2. You're basically taking the average of the two numbers when you look at the midpoint. When you have a bunch of different numbers and you want to take their average or their mean, you can just add them all up and divide by the number of numbers you're taking. So in this case, if you have two numbers, you're taking the average of, add them together, divide by 2, that'll give you the midpoint. So here's a question. Let's say we have a number -1 on the left and some number, call it x, over here on the right. What would be the midpoint of -1 and x if we were to use this formula?
Would it just be -1 plus x divided by 2?
Yeah, it's going to be -1 plus x all over 2. Hold up. What if I had -1 and, I don't know, e sub n? What would be the midpoint of those? E sub n minus 1. What would be the midpoint of those two numbers?
-1 plus e sub n minus 1 over 2.
1 plus e sub n minus 1 all over 2. Where have I seen that before? So, another way we could have actually defined the sequence instead of using this formula is we could have said, let's let e sub 1 equal 1, and for n greater than 1, e sub n is going to be the midpoint of -1 and the previous term in the sequence. Because if we wanted to do that, and we wanted to start maybe graphing out what do the terms in this individual sequence look like, well, our first term is at e sub 1 equals 1. Joanna, what number is halfway between -1 and 1? Yeah, so our second term is going to be here at 0. Sarah, what number is halfway between -1 and 0?
Negative half.
Yeah, we're going to get -1/2 here for our third term. Mary, what's halfway between -1 and -1/2?
-3/4.
Yeah, it's going to be -3/4. And then E5 will be halfway between E4 and -1. halfway between E5 and -1 will be E6, and then halfway between those two will be E7, halfway between those two will be E8. Just looking at this number line, Joy, what would we expect the sequence to converge to? Yeah, looks like we're getting closer and closer to -1 if we keep taking the midpoint between -1 and our previous term each time. So that would be sort of like a geometric way you could think about this problem that ends up giving the same result as what James got from his plug in a bunch of values for n and see what happens approach. Which essentially is what we did there too, but using kind of the idea of taking a midpoint each time. Sometimes there's fun geometric ways you can look at sequences in the next few standard series like this, where you can sort of see this sort of geometric pattern to help explain what's going on algebraically. And that's something I really like about math, is when you have cool ideas from like, you have something that you can see in algebra, but you can also see the same result using a different sort of perspective. Questions, comments, concerns? And meaning sequences. Sorry, I didn't expect to spend so long talking about the sequence. I probably should give me more room on the page to write stuff down about it. Okay. So let's look at it. So next thing I want to do is I want to look at a specific class of sequences. That being a type of sequence that's called a geometric sequence. Where the idea behind a geometric sequence is we have a sequence where we start with where we're going to start with the formula a sub n equals r to the n for some constant r. Meaning, if we wanted to look at individual terms in our sequence, they would look like r, r squared, r cubed, r to the fourth, and so on. So I'm going to look at a couple of these different types of sequences and see if we can figure out when is this type of sequence going to converge, when is this type of sequence going to diverge. So let's start off with r equals -2. So if we were to look at r equals -2, we would get a sub n is -2 to the n, which is going to give us -2, -2 squared, -2 cubed, -2 to the fourth, and so on. So -2, +4, -8, +16, etc., etc. Kate, Central Kate. Central Kate, I like that name. I don't know, don't ask me why. Is that going to be a convergent or a divergent sequence?
Divergent.
Divergent, why is that?
It doesn't approach any value, it just oscillates.
Yeah, it just kind of oscillates back and forth, and the oscillations are getting bigger and bigger as time goes on. So this would be a divergent sequence. Ty, what would be a value of r for which you think the geometric sequence would give us something convergent instead of divergent?
Maybe would 3 work?
Would 3 work? So if we did 3, we'd get 3, 9, 27, 81, 243.
Oh, would it? Probably fractions would work better, right?
Like what?
1/2.
So if we had r equals 1/2, that would give us something like a sub n is 1/2 to the n, which is 1/2, 1/4, 1/8, 1/16, etc., that converge?
It looks like it converges to 0.
I would agree. This is going to converge to 0. All right, activity time. I want you all to take a couple minutes, talk to your neighbors as always, see if you can find out for what values of R does this converge, and for which values of R is the sequence going to diverge. So it diverged at R equals -2, it converged at R equals 1/2. See if you can tell me, out of all the real numbers out there in the wild, which ones can we plug in for R in order to get a convergent geometric sequence, and which ones can we plug in for R that will give us a divergent geometric sequence? So go ahead, take a couple minutes, talk to your neighbors, and see if you can answer this question. I'll give you an, it's not as simple as is R positive or negative.
Right, 'cause it's getting smaller and smaller and smaller. It's getting less positive and negative. It's getting smaller and smaller.
Where it goes back
That's always a good place to start. If you're not sure, try a few example numbers, see if you notice the sort of pattern.
Fractions converge.
Experimentation is a great way to notice patterns.
I just included negative one.
Yes, Nathan? Click your partner. I wish I could as well. Say it, send it to the recording if you ask one.
If it's like repeating, if like the sequence is just repeating the same number over and over, like if it's just like one, okay,
So I
What does your intuition tell you?
And so if it's bigger than one, then it's always like some number where the numerator is greater.
Yeah. I would say that if you have a sequence that's constant or eventually constant, like 1, 1, 1, 1, 1, I would consider that to be a convergence.
So that will just shoot up.
Technically, it's not getting closer to 1 as time goes on, but only because it can't get closer to 1. It's as close as it's ever going to get, which is at being at 1. Yeah, good question, dude.
So if it's bigger than 1, it's like some number where like 4 over 2, yeah, where this is bigger than this, so it grows faster. Yeah. That has to be one of the three. Yeah.
have some competitors. If R is less than -1 and greater than +1, holy moly. I can't think of many R's that'll do both of those things. Alrighty, let's come back together and talk about this for a couple minutes. So, looking at the question of for which values of R is this sequence going to converge? Anybody notice any patterns? Ty, I saw you and Gabe were kind of working on coming up with some stuff for R earlier. What did you all decide?
So we kind of decided that if R is less than or equal to -1, then it diverges. Or if R is greater than 1, then it diverges. And so I guess that would mean that if R is between 1 and less than or equal, like it's greater than -1 and less than or equal to 1, it converges.
Okay, so you sort of had three separate cases. The case where R is greater than 1, less than or equal to -1, or between -1 and 1. And you said it converged only in this case and diverged in the other two. What led you to that conclusion?
Well, if R equals anything -1 or anything like less than -1, then it's going to be an oscillating type of function because it's going to go like 1 -1 1 -1, or it'd be like -2 4 -8, and so it would not converge to anything.
Yeah, I'd say if R is less than -1, then when we take R, R squared, R cubed, R to the 4th, etc., we're going to get bigger and bigger oscillations as time goes on. Because it's going to constantly be going back and forth between negative, positive, negative, positive, negative, positive. And so in that case you would say divergent. Sounds good. What if R is equal to -1? I'm going to split this up, Ty, a little bit more than I think what the two of you did. Roden, what happens if R is equal to -1?
It oscillates, so it goes back and forth, so it's divergent.
What kind of oscillation though? Is it bigger and bigger oscillation, smaller and smaller?
It's just the same, it goes 1 -1 1 -1.
Ah, we get -1 1, -1 1, -1 1. We get oscillations that don't change in magnitude, and it's still going to be divergent. What if R is between -1 and 0? Maria, what happens in that case?
It'll converge.
Do we still get some oscillations going on?
Yeah, it'll oscillate around the x-axis. It's 0.
It's oscillating, but still going to 0?
Yeah, because it goes to smaller and smaller values.
Ah, because it's smaller and smaller oscillations? Yeah, in that case, when we take, like, if we were to take, like, -1/2, for instance, we would get, like, -1/2, +1/4, -1/8, +1/16. We'd be getting oscillations. But they'd be getting smaller and smaller as time goes on. And I would agree, I think we could say that's going to converge to 0. So if R is negative, then negative values of R between -1 and 0 will cause the sequence to still converge, but R less than or equal to -1, as Ty pointed out, I think will lead to divergence because you get oscillations that don't settle in on a single number. Unlike these oscillations here that are getting smaller and smaller and smaller as time goes on. Okay, so Ty, you said you noticed something pretty similar happening for positive R's as well? Like that R equals 1 was sort of the tipping point for you?
Yes.
Okay, yeah, I would say so. At 1/2, we had these sort of terms that are getting closer and closer to 0. And I think we can say that if 0 is less than R is less than 1, then when we take R squared, we'll include 0 in this, R squared, R cubed, R to the 4th, etc., we're going to be getting terms that when we take like 1/2 times 1/2 times 1/2 times 1/2 over and over, we're going to be getting numbers that are getting closer and closer and closer and closer and closer to 0. What happens if R is greater than 1? Hold on. Joanna?
It's gonna diverge, cause it's just gonna keep going.
Yeah, if we had something like R equals 2, as we keep multiplying R by itself, we'd be getting bigger and bigger and bigger, like 2, 4, 8, 16, and so on. We would have something where it's like starts off, I don't know, here, and then when we keep multiplying by itself, it's just going to keep getting bigger and bigger and bigger, exponentially, in fact. And so, Devin, what case does that leave us with? We've handled all the negative R's. We've handled R between 0 and 1. We've handled R greater than 1. What number does that leave us with that we still need to check?
1 itself.
Yeah, at R equals 1. So if R is equal to 1, and we look at 1, 1 squared, 1 cubed, 1 to the 4th, ... going on forever, it's going to give us a sequence that looks an awful lot like a bunch of 1s and nothing else, because 1 to any power is just 1. And Phoebe, you'd asked me about this earlier. What were your thoughts on this one?
I said that it converges on 1 because it can't get any closer, and you agreed.
And I did agree, as it turns out. Yeah. Even if you have a sequence like this, it's just a constant sequence that's always the same no matter what you plug in for n. You would consider that to be convergent to that constant value. Technically, a sub n is not getting closer and closer to 1, but that's only because if you're already at 1 and you stay at 1, you can't get closer to 1. You're literally there. It's like your GPS can't tell you you're getting closer to your destination if you're sitting at your destination. So to sum up, I would say that the geometric sequence is going to be convergent if what? If R is between -1 and 1, including 1, but not including -1. Because at 1, we just got the 1, 1, 1, 1, 1, 1, 1 converges to 1. At -1, Maria pointed out we just have this sort of oscillation that's not getting any bigger, but it's also not getting any smaller, so it's still going to be divergent. So it'll converge if -1 is less than R is less than or equal to 1. It'll diverge if R is less than or equal to -1, or if R is greater than 1. Any questions or comments? I bring up the sequence now because in the next standard we're going to have a fun time looking at what happens if you take a geometric sequence and you add up all the terms in the geometric sequence. So like if you were to take 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4th and so on. Turns out that gets into some spicy behavior. And with that, one last sequence that I would like to look at for today. Well, in this standard at least. And that's going to be the sequence. A sub n is going to start with square root of 3. Second term is going to be square root of 3 square root of 3. The term after that is going to be square root of 3 square root of 3 square root of 3. And then we're going to have square root of 3 square root of 3 square root of 3 square root of 3. And so on. My question is, does this sequence converge? And if so, what does it converge to? So this is an interesting type of sequence, in that it's not, in that you can kind of immediately picture what every term looks like. If we were to look at the 10th term, it would be, I'm not going to write it out, but it'd be like, you'd have like square root of, you'd have like 10 different square roots going on in 3s at different stages in all of them. And it's unclear to me, is that even going to give us a number or not? So the first thing I want to ask is, does this sequence actually converge? So let's take a look at it. So if we were to start graphing out terms in this sequence, we would get interrupted by those gigglers out in the hallway. And then after we take care of them, we get a sequence that looks sort of like this as time goes on. Where the sequence grows more and more over time, but as time goes on, the rate at which it's growing is getting smaller and smaller and smaller. With that in mind, James, would you expect that this sequence would converge or diverge?
I assume it converges, but it could also be like a natural log function.
Yeah, just because it grows slower and slower doesn't necessarily mean it's going to converge or diverge. Because there are functions like if we define a sub n as, let's say, natural log of n. If we started graphing those numbers, it's going to grow at a slower and slower rate. Yet this would still diverge. It would still go to infinity as n goes to infinity. So for this sequence, we could have something like the natural log function. We could also have something like, I don't know, 1 minus 1 over n. Whereas n gets larger and larger, that would converge to, say, 1. Even though it keeps growing forever, but at a slower and slower rate. So how do we determine this? I'll give you all a hint. Turns out that if we were to sort of try and graph out the sequence, it almost has like a horizontal asymptote in a sense. And that there's some number, a, that this sequence is never going to get bigger than. Unlike natural log, which eventually will grow towards infinity, this sequence never gets past this one line here at y equals some value a. Does that change your answer, James?
Yeah, because then it would converge.
You think it would converge? Just because it never passes some line, that you think it means that has to converge?
I think so. Because then it could only get closer and closer to that line, unless it eventually like dips down or something.
Is that ever gonna dip down, you think?
I don't think so.
Yeah, no, it's always gonna keep growing forever. And what James has happened upon is actually a fancy theorem that we actually talked about recently in my real analysis class called the monotone convergence theorem. Which is a theorem that says that if you have a sequence that's always increasing or decreasing, which this one is an always increasing sequence, but doesn't go to positive or negative infinity if it's kind of bounded in a sense. Then the sequence will have to converge. And so I would say this sequence doesn't go off to infinity, it's bounded above on how big the individual terms in the sequence get. And it's always increasing. If you add another square root of 3 at kind of the innermost part of the expression, you're always going to be making it just a little bit bigger. Therefore, by the monotone convergence theorem, I would argue this sequence does in fact have to converge to something. So follow-up question. If we know the sequence converges, how do we determine what it converges to? I think.
Is there any way we could maybe write it with fractional, with like exponent, so that we can see maybe more of a pattern going on, like 3 to the 1/2, times like 3 to the 1/2 times 3 to the 1/4.
Ah, that's certainly a way we can think about it. Yeah, we could certainly try and do that. So what Bethany's proposed is that we try and rewrite this as just each term is some power of 3, it sounds like. So if we were to take a sub 1, which is just square root of 3, how could you write that as a power of 3?
3 to the 1/2.
So that's going to be 3 to the 1/2. How about a sub 2, which is 3 square root of 3, but you're taking the square root of all of that.
3 to the 1/2 times 3 to the 1/4.
Yeah, that's going to be the square root of 3 to the 3/2, which is going to be 3 to the power of 3/2 times 1/2, which will give us 3 to the 3/4. Or as Bethany put it, you could write that as 3 to the 1/2 times 3 to the 1/4, which will give us 3 to the power of 1/2 plus 1/4, and that would give us 3 to the 3/4 in the same way. All right, Bethany. How about the third term? Square root of 3 square root of 3 square root of 3.
Would it be like the same thing we had before, where it's like you multiply 2 in the denominator, and then that's n, like.
Yeah. If you notice, this expression right here, just this piece right here, is the same thing as a sub 2, which Bethany saw was 3 to the 3/4. Turns out, A sub 3 is just square root of 3 times the previous term. If we write that out, we'll get square root of what? 3 to the power of 1 plus 3/4, which is going to be square root of 3 to the 7/4, which is going to be square root of, no, not square root of that, just 3 to the 7/8. And then if we were to take a sub 4, we could similarly get 3 to the power of 15 over 16. A sub 5 is going to be 3 to the power of 31 over 32, and so on. Is anybody noticing a pattern looking at these terms? 3 to the 1/2, 3 to the 3/4, 3 to the 7/8, 3 to the 15/16, 3 to the 31 over 32. I don't want to have to call on James. What's sort of the pattern that's going on here? We're looking at the different powers of 3 that show up. Joy?
It's getting closer to 1.
What's getting closer to 1?
The exponent.
Yeah, looks like these individual terms are getting closer and closer to 3 to the power of 1, which is 30. And in fact, that is the limit of our sequence. This sequence of crazy looking square root expressions, which you might guess would converge to something horrifyingly nasty, no, it converges to 3. Alright, confession time. Bethany, the approach you took was not what I had in mind for this one. It totally worked though. It gave us that nice result. I'm gonna show you all though what I came up with when I tried to look at this sequence as well. Because I think there's several ways you could think about this. So the way I thought about this is if A sub n converges to L, based on the monotone convergence theorem, we know that the sequence has to converge. There has to be some number L that it converges to. If you notice, A sub 1 is square root of 3. For n greater than 1, I think we could find a recursive formula for A sub n. And the recursive formula, which I sort of use, Bethany/I sort of used here, A sub n is always going to be equal to square root of 3 times A sub n minus 1. Because to get from each term, like if this is our A1, here's A1 right here, you take square root of 3 times A1 in order to get A2. You could take square root of 3 times A2 to get A3. You could take square root of 3 times A3 in order to get to A4, and so on, which gives us a nice kind of recursive formula for looking at the sequence, I would say. So with that in mind, how do we find out what L is? Well, we know that L is going to be limit as n goes to infinity of the A sub n's, right? That's just the definition. You take a limit as n goes to infinity of the nth term in your sequence, that'll give you the limit of your sequence. That's going to be the same as taking a limit as n goes to infinity of square root of 3 times A sub n minus 1, using our recursive formula. So we can pull the limit inside of the square root here. mainly because square roots are continuous functions. And just take square root of 3 times limit as n goes to infinity of a sub n minus 1. And here's the question. Gabe, if L is the limit as n goes to infinity of a sub n, what would you expect the limit as n goes to infinity of a sub n minus 1 to be equal to? So this is a tricky question, which is why I had to call on Gabe for it.
Infinity.
That goes to infinity?
N minus one goes to infinity of n.
N minus 1 goes to infinity, but how about the n minus first term in our sequence? So if the nth term in our sequence, if a sub n is going to L as n gets bigger and bigger and bigger, if the nth term in our sequence is approaching L, what's the n minus first term going to be approaching? It's not going to be infinity. Bethany?
0?
It's not going to be 0. Okay?
L divided by 3 squared.
It's not going to be L divided by 3 squared. Getting closer. Aiden?
Is it just L?
It's going to be L. And the reason for that is that if you look at, if the limit as n goes to infinity of a sub n is going to be L, we would expect the limit as n goes to infinity of the previous term in our sequence to approach the exact same value every time. So if we wanted to look at an example of something like 1/2, 1/4, 1/8, 1/16, 1/32, ... Anna, what did we say that that's going to converge to?
0.
Going to converge to 0. So this is A1, A2, A3, A4, A5. So that sequence converges to 0. What happens if we look at the previous term in the sequence as n goes to infinity? Instead of starting at the first term, it's like we're starting at term 0. Well, we have some A0, which doesn't really exist. But then we would have A1, which is 1/2, A2, which is 1/4, A3, which is 1/8, A4, which is 1/16, and so on. Ignoring the fact that we don't have our first term in the sequence, Taylor, what would you say this sequence converges to? Yeah, basically by the exact same logic. When we take a limit as n goes to infinity of the n minus first term, that's still going to be looking at a limit as n goes to infinity of the nth term, but just you're one term behind. You're lagging a little bit, but you're still having the same behavior. All right, I know we're out of time. I promise you this will be really quick. So with that, we get the formula L has to be equal to square root of 3 times L. And if we wanted to solve for L, we could square both sides to get L squared is equal to 3 times L. If L squared is going to be equal to 3 times L, how can we solve that equation for L? Reagan, how would you solve that for L?
Put the terms on the same side.
Okay.
Equal to 0.
Sounds good. And then we could factor the left-hand side to get L times L minus 3 is 0, which means L has to be 0, and clearly this sequence is getting bigger, so it's not going to be 0. Or it has to be 3. We get the same answer that we got using the Bethany approach. All right, that's it for Standard 10. So on Friday, we'll take our, so I'm not gonna ask you anything like this crazy sequence on the end on like a standard 10 quiz or anything, or retest or anything. Instead, what you can expect for Friday's quiz will be, I give you a couple more simple sequences and ask you, do these sequences converge or diverge? If they converge, what do they converge to? Okay, hope y'all have a good one. I'll see you all on Friday. Sorry to end a minute or two late here.